Okay, so welcome back everybody. We've gone ahead and trained our model using our split of our X and our Y data. And we have gone ahead and made predictions. So we can take a look here. There's where our split is. There's no outcome of train test split. You certainly could test it just if you wanted to make sure that everything is okay and that everything worked fine if you'd like to. If you want to take a look at maybe just a quick head, you certainly can. So, there's 4 of these values that actually came out of this. Again, this is our ground truth. This is what we use to make predictions. And our X train and Y train are what we use when we actually fit the data. So in our last video, we instantiated, brought in our decision tree regressor, limited to a maximum depth of 5. You'll see what that is here in just a few minutes. We actually fit it or trained it on the training data, and then we used our features in the test set to actually make predictive outcomes. So in this last video, or this next to last video, I've actually opened and run all of these cells for you because the very last video is just going to be a summary. And I wanted to show you kind of what our findings were since we're only building one model here. So now that we have predictions and we still have ground truth, right, which is our Y test value that's sitting out here. Matter of fact, if you want to take a look at that, let me show you what that looks like. So if we take a look at Y test, you can see these are the known values that are in the data set. So what we did was we made predictions. I can come down here and show you while we've got them both on the screen. We made predictions, and these come out as an array. They're not in a data frame, but we made predictions from these same rows, the features that were in these same rows. So you can see in row number 24301, the real value is 4.17. My predicted value was 4.077. 4.17, these are taken 15 minutes apart. Let's jump down to this 802 number. So that's the third value. Looks like 802 here, my model predicted to be 768. That's where the error comes into this model. We talked a little bit about error earlier, right? The concept of error in a regression problem. You're never going to nail these things down in a perfect one-to-one relationship unless you have perfectly related data in the features, or maybe your data set is so small that it's not really useful for machine learning. So anyway, let's dive into how we now assess this in a real world way. So we have 2 different assessments for this. We have something called R squared and something called RMSE. And by the way, these are not the only ones. The default assessment is actually in scikit-learn is something called mean squared error. And basically that's an average of all of the errors is what it is. We want to get it sort of in the same unit as what we're working on. So we do RMSE, and that way we can relate the amount of error to something that's sort of real world, and that's what our Y value is in. And again, there are tons of these different assessment values. You're going to see these, sometimes they're called cost functions, sometimes they're called loss functions, depending on how they're actually used. Sometimes those are interchangeable, sometimes they're used when you're talking about the catalyst of different machine learning problems. So those are two things you need to really dive into if you're going to get deeper into machine learning. But no, for now, R squared is actually, this is a D on the end of it, R squared is actually a percentage of the amount of variation in your data that your model actually understands. So we want that R squared number to be as close to 1 as possible. It's a range between 0 and 1. And we can convert this decimal over to a percentage. So what it's basically saying is our model that we built understands about 81% of the variation of the data. That's a good thing. Building a model that can generalize well when you feed it new data, the higher the R squared is, the better it's going to be at that. Okay? Unless it just learned the data that it was trained on perfectly. and then it can't relate to new data. That's called overfitting, and it's something we'll go through in another exercise. Also, you have an inverse of r squared just methodically. As the r squared rises and your model understands and is training appropriately, understands more and more of the data, the error between your predictions and your real values should actually go down. And that's what RMSE is. And you can see here, I've made this conversion. We're sitting at around 113 watts per meter squared of solar radiation in error. Considering that the highest you can get on a really sunny day in Arizona is probably around 12 to 1300 maybe watts per meter squared, you know, you're looking at around, what is that, around 8%, 7% error. And given that most of your solar panels are nowhere near that efficient, it's actually really good. So you got a good performing model here. If you didn't, you'd have a lot of work to do. You'd start the process over. You go back to pre-processing. You go back to identifying your X's and your Y's, or your Y value. You might want to take some of those things out. You might have to combine some of those things. There are different things you can do to data. All of that is sort of the study, right, of data science and machine learning. And getting the data prepped and ready for the model, for modeling, is about 60 or 70% of the entire process. Really just applying the model and knowing which one to use and then tuning it properly is the last little piece. So now that we've assessed this and we know that we have a good model, how do we do something with it? This is that other piece. I told you when we started, there are two difficult pieces of machine learning. Understanding the problem and turning it into a machine learning problem, and then telling the story with it, turning it into business value, right? So we've been asked by climate scientists to build this model and kind of pull it apart so we can tell them, things about it. So let's see how we do that. So since this is a decision tree algorithm, we can actually view the decisions that the algorithm made while it was training. Now, I've given you two different examples of this here because decision trees can get really big. This is not a huge problem, and you can see, even though I've limited it to only 5 different levels, you can see the 5 different levels here, 1, 2, 3, 4, and 5. The dependent variable, or your Y outcome, is down here on the very bottom. And again, this lesson is not about how to read this tree. I have some resources at the bottom of the notebook that will help you do that. But this is how you see the tree. Well, you can see that we've plotted it out, and I've even called this too much cowbell. Maybe I'm dating myself. That's a Saturday Night Live reference. But if you're a Christopher Walken fan, you'll get that. So that's really too much for it, right? We could print this out to an image, and we did, but for the purposes of a Jupyter notebook, I wanted to be able to show you kind of do this twice. So I built the model again, and I reduced the number of levels that it actually used this time, and built it a second time. Now you can really see the tree well, and now we can begin to understand some of the things about this data. And I didn't do anything as far as magical or even statistically relevant to tell the decision tree how to be built, other than controlling how big it was. That's all I did. And remember, this decision tree is around 81% accurate and has relatively low error. So we know what we're looking at is valid. That's something you have to be careful with on a decision tree, is you can build it at any time. Well, your model might be 20% accurate, or 20% understand 20% of the variation of the data, and you can still plot it out. Doesn't mean the rules are worth anything. So only plot out that, decision trees that come from really good models, because then within a relative probability, like all of this is dependent on what you're looking at, up to a certain point can be taken as real, somewhat real. So the decision tree, in the way that it makes its decisions, has decided that air temperature, out of everything else in this data set, with respect to solar radiation, air temperature is the most relevant input in this model. That's extremely important for understanding solar radiation. That's saying we can delve from that air temperature impacts solar radiation more than anything. It's not causal. We don't know that. It's not causality, but it does, according to the data, it is related to it in some type of way, more than any other feature. Okay, and that may just be mathematically, but again, that's not causal. Don't get this screwed up with causation, right? We're just reading the tea leaves, so to speak. In this case, the nodes. That's an inside joke. The bottom rectangles are called leaves. So we start with air temperature. This is a decision tree, and it makes decisions based on binary splits. When the air temperature is less than 76 degrees and the humidity is less than 53.15, and the time of day is less than, this is basically less than 5 o'clock. This is in 24-hour format. Then you can expect your solar radiation to be around 452 watts per meter squared. Remember, you got some error in there, right? So you could have, you could be off by around 100 watts per meter squared. Anytime less than that time or greater than that time, then your value, and that makes sense because it's getting dark, right? Your value tends to average around 41.7. So anyway, you can see that's, that is an example of a decision tree. And there, we can see that air temperature, humidity, time of day were very relevant, right? We don't see things like barometric pressure in here at all. And even though I limited this tree to a maximum depth, I didn't limit it to the number of features that it used. I could have done that, but it picked the relevant ones that were needed to build a tree to this depth. So air temperature, humidity, and time of day were the relevant features when you're limiting it to this depth. So you've got three really high-end features there. So let's look at what those are. This is another really important thing cool thing you can do with a decision tree is you can actually unravel it. If you know you have a well-performing model and someone wants you to replicate that, you can actually unravel the decisions that a decision tree made and look at how it treated the features in making those decisions. This is extremely important for things like marketing analysis and sales analysis. When you've got multiple actions and outcomes that someone wants to spend money on or not spend money on, you can replicate this model. Maybe you're saying, okay, I want to predict, 85% sales or volume in my sales margin, next year. What do I need to do that? Well, if you're building a model that can replicate that, at least you can unravel the features. If those features are different initiatives and you've got some historical data on those, you can at least unravel those features and present to a stakeholder where they may or may not spend their money to replicate what that model actually does. Have to be careful doing that, but in theory, that's really good for feature importance, right? Something else that's really the benefit of feature importance is you see how these things are ranked. So feature 0, which in our case was air temperature, the model treated it as around 0.41 priority. If you want to convert that to a percentage, that's fine. You'll see eventually a lot of these will fall off. The second one, which was humidity, was around 39, and then the last one, which was time of day, which is around 19. You'd think time of day would have probably been the highest on here, and it's actually the lowest. And because I limited this to a certain depth, the last two were not utilized. The predictions were made after the third feature. But this is also a really good way for you to see how your model treated things, right? We go back up there and think about correlation. We talked about how related X values can have highly correlating values. Well, maybe you look at this feature importance and it's only got one feature in it. And it's, this all of a sudden has one score and it's 0.98 and all the rest of the features weren't even used. Well, right away that model's not going to be very valuable, or you've got some poor data that you've got to go work on. So it's a really good relevant way of checks and balances to kind of make sure that everything is working appropriately the way it was designed to. So anyway, that's the end of this particular Learn by Doing exercise. I tell you what, rather than making one more video, let me just sum it up here because I know we're running a little long. I got some resources here at the very end. I put together a quick presentation not too long ago on decision trees. If you want to dive into sort of what these are and how they operate, I've got a really neat little Plinko exercise in here if you're a big fan of The Price is Right. But this, download this if you'd like. View this in full screen format because it's got a lot of animations in it. It'll kind of walk you through what decision trees are. I've got another exercise, another reference here on R-squared and regression and root mean squared error. These are two things that are really important if you're going to pick up and go from this point forward, because the next exercise that's sort of useful in the list, rather than diving sort of into the math behind everything, go ahead and work a classification exercise next. You can use this same notebook for a lot of the things that are in it, except the algorithms will change and some of the way that you pre-process will change. But I would probably do a classification algorithm next, and then I would stop and get into the math behind these things. I always tell my students, because most of them don't have a math background, the math behind these things are extremely important. You don't have to be a math major to dive into this stuff, but at least have an extreme conversational understanding about what's happening at a functional level. You're going to have to go through a data science interview, or you're going to have to go through an ML interview, or whatever it is, and you're going to be asked those things. So, don't just stop at sort of the tool level understanding of this. Get into the math. And if you have to read some on linear algebra, or if you have to read some on calculus and get into derivatives and things of that nature, do that. No one's telling you to go out that you have to take math classes, but get a general understanding, a functional understanding of how these algorithms work. I tell my students, tackle one a week. That you ought to be able to dedicate that kind of time. Visit with me, visit with your mentor, visit with your instructor if you're on campus. Ask them to give you, at the beginning of the semester, give me the algorithms we're going to learn this particular session, this particular semester, whatever it is, and break that down equally over the course of the session. And that's what you need to focus on, because it's like this. You can have the best tool belt in the world, but if A, you don't know what problems to use it on, and B, you don't know how to use the tools themselves, and that includes when to use what tool, none of this is going to be valuable for you. So thank you so very much. Really, really enjoyed creating this for you. Hopefully you have found it to be beneficial. My information is here in the resources along with this presentation, not listed on the screen here, but in a text file in the resources. If you need me for anything, please visit with me, catch me on LinkedIn, shoot me an email. Happy to answer any questions any of y'all have, and thank y'all so much. Best of luck on your continued journey in machine learning. Thank you so much, everyone.